Hello everyone, my name is Sultan and I'm here to present our work titled Kerveros, Efficient and Scalable Cloud Admission Control. This work describes Kerveros, the admission control system that is actively deployed at Microsoft Azure. This work was done in collaboration between Microsoft Research, Microsoft Azure, and Penn State. In recent times, global supply chain shortage has had major negative impact across different sectors, causing inconvenience for both the customers and businesses. And large-scale cloud providers have not been immune from it. In face of such unprecedented shortage and increased demand, it has become more important than ever to accurately track resources in the cloud systems. Accurately measuring available resources is an essential question for the cloud admission control, and it can be very hard given the extreme scale and diversity of the cloud environment. In this talk, we focus on Microsoft Azure, which is one of the largest cloud providers in the world, with millions of machines spanning hundreds of data centers across the globe. The cloud is a highly heterogeneous environment with many different zones varying greatly in size and hardware variety. As a result, there might be temporary shortages with specific hardware types and zones based on demand. In particular, with thousands of VM types of various sizes, it is difficult to pack all resources together and know how many more VMs can fit. Among the different size VMs, the smaller VMs can be easier to pack, while the larger are much more tougher. Moreover, cloud providers have recently introduced capacity reservation features where customers can purchase guaranteed capacity in availability zones for future usage. To clarify, the capacity reservations shown here are for demonstration purpose only and do not get bound to any hardware before being claimed. Similarly, cloud providers also need to reserve capacity to handle failures and maintenance. The reason behind that is to ensure when the VMs fail or undergo maintenance, they can be migrated to reservations for healing. Given all these resource reservation and heterogeneous constraints, cloud providers are faced with the question of whether they should accept a new request. Is there enough space in the availability zone to accept a new request without running out of resources that were already promised? On the face of it, this seems like a simple problem since it involves checking how many available resources are left based on the total minus allocated resources. But the problem is a lot harder than one might assume. There is a lot of variability that affects both supply and demand over time. The supply of resources is affected by different types of failures along with scheduled and unscheduled maintenance. At the same time, the demand is dictated by VM requests, capacity reservations in the system, and scale-out demand from existing tenants. For example, we can see from the plot of production data that in the short term, the VM requests are highly variable and can have abrupt spikes time to time, putting strain on the resources. The demands can also change in the long term due to various macroeconomic conditions such as pandemic, recession, emergence of new technology, and the supply of resources has a hard time keeping up with that. The heterogeneity in hardware and VM types in Azure makes this even harder. Here we have a small peek at the wide variety of VM sizes offered in Azure, starting from small VMs having 1 core and 2 gigabytes of memory to super large VMs using 448 cores and 24 terabytes of memory. And this wide range of sizes makes packing VMs in the cloud much harder, which in turn makes the admission control much more difficult. Here we see only a few of the VM types, but in reality, Azure supports more than 1,000 VM types. And here on the right plot, we see the distribution of number of VM types across availability zones, and we see that over half of them support more than 900 VM types each. On the left, we see the distribution of the number of hardware types, where some zones have up to 40 different hardware types. And this high degree of heterogeneity in Azure leads to fragmentation in the system, which makes estimating resources even harder. Another challenge for admission control is the placement constraints spanning across the whole topology of Azure. This introduces the challenge of calculating resources in different locations among different resource combinations. The users can also place additional constraints based on locations, such as having multiple racks in the same fault domain, multiple machines in the same cluster, etc. And the admission control system needs to handle all this while being fast and scalable to meet the throughput goal of more than 120,000 requests per minute, while maintaining an average latency in the range of 5 to 10 milliseconds. This also needs to be efficient, as even a 1% gain in resource efficiency leads to more than $100 million per year in savings. And our solution to all this is Kerveros, which does admission control at the large scale of Microsoft Azure. The main idea behind Kerveros is the late binding of reserved resources for admission control. Late binding in this context means to not bind resources that are reserved to any specific hardware at admission time, rather when they are claimed. What makes late binding appealing for this purpose is that it ensures high packing efficiency in the cloud systems. This is achieved because late binding makes resource allocation decisions when the resource is required, and hence makes the best allocation decision at that point in time. It also enables accurate accounting while tracking resources across various VM types. Also, late binding provides flexible packing, as it can easily take the best allocation decision at the allocation time and not be bounded by any earlier choices. Moreover, as it does not have to allocate resources at admission time, the admission process needs only check available resources and therefore is really fast. And on top of all these, late binding allows reusage of unclaimed reserved resources as spot VMs to maximize ROI. But late binding comes with some challenges, which we will explore now. Let's show the challenges with an example. Let's assume we have a 2-machine cluster with 100 capacity each, giving us total capacity of 200. There's already an unclaimed reservation of size 120 in the cluster, which was made for guaranteed capacity in the future. Let's say a new VM request of size 50 has arrived for admission into the system. Given that the available capacity in the cluster is greater than the request size, it would be intuitive to say that the cluster can surely admit the request. But is that really the case? Let's assume the unclaimed reservation consists of 6 reservations of small VMs of size 20. Now the new request is admitted based on the condition checking. Now, after the request is admitted, let's assume the customer comes to claim the reservation. And in this case, claiming the reservation works, as there are many different configurations in which the reservation can fit in the cluster. Now let's consider another scenario where the unclaimed reservation consists of 2 large VMs of size 60. Now, if the customer comes to claim the reservation of the VM of size 50 is admitted into the cluster, they won't be able to do that. And this would be a direct SLA violation, as the customer would be denied resources that they were previously promised. What is apparent from this example is that admission control must take the shape of the reservation into account while making decisions. And Kerveros' solution for incorporating that is allocable VM. Allocable VM is Kerveros' novel bookkeeping technique that is facilitating accurate accounting with late binding. It basically tracks how many additional VMs can fit in the system for each VM type. And it converts multidimensional resource demands to single dimension. For example, from this table, we can see that each VM type has multidimensional resource requirements consisting of CPU, memory, disk, and many more. Allocable VM converts this multidimensional count to a single number, which facilitates fast and accurate accounting. And we have developed 2 algorithms that adjust AV count for reserved capacity, CRA and LAA. We now describe how these algorithms for accounting work and how they are used in making admission control decisions in the system. In Kerveros, we have multiple load-balanced allocation worker instances that do allocations. Each instance consists of request handlers, an AV count estimator, and an in-memory VM placement and reserved capacity state snapshot. The request handler does zonal admission control while considering all reserved capacity in that zone, and it handles both the VM and reservation requests. So how does the request handler work? When a request arrives, it checks the AV count. If there's enough AV count in the system, the request is admitted, and the VM placement and reserved capacity state is updated in the placement store. And if there isn't enough allocable VM in the system, the request is rejected. But how do we get the AV count in the first place? The AV count estimator calculates and updates the AV count in the zone. First, for each VM type, it initializes the AV count by counting how many VMs can fit in the remaining space across the zone. It uses an in-memory snapshot of VM placements to determine how much space is left in the zone. The AV count is computed independently for each VM type, assuming no other VM types come. For example, the AV count for small VMs is counted, assuming no medium or large VMs will come. And if they do, the AV count for small VMs will need to be adjusted accordingly. The next step is in the AV count estimation is to subtract the AV count for the existing reservations in the zone. As we have mentioned above, this will need to convert between different VM types to account for how a reservation of one VM type reduces the available capacity of other VM types. And this is why we call the AV count estimation the conversion ratio algorithm CRA. It handles multidimensional conversion by using AV count to determine the conversion ratio. And these are very fast, so the AV count estimation can be done quite frequently, occurring every minute. So the CRA enables fast and scalable admission control decision. But while converting between VM types, it suffers from errors, such as rounding errors causing fragmentation. And by design, this rounding tends to be conservative to prevent SLA violations. But it leads to resource wastage in the system. So how do we mitigate that? The inaccuracy in CRA is mitigated by using linear adjustment estimator. It shares the same components with allocation worker instances to have allocator capabilities. And it uses request generator that generates synthetic requests to see exactly how many VMs of each type would fit in the system. This way, we get a more accurate accounting of AV count for each VM type in the system. Afterwards, the VM count for all VM types are sent to the ML platform to learn the new parameters for calibrating the CRA estimates to better reflect the correct AV count. This whole process is time-consuming and hence done every 30 minutes. And this emulation and CRA calibration fall under linear adjustment algorithm LAA. This does accurate accounting of resources, leading to high resource efficiency, but it is slow and compute-intensive, hence only done periodically. And all these components in Kerveros need to share information among each other, which is done via a PubSub platform. So Kerveros uses a fast component that enables scalable admission control in Azure. And to mitigate the inaccuracy in the fast component, it uses a slow component that provides accurate accounting of system resources. And with the combination of these fast and slow components, Kerveros achieves the goal of fast and resource-efficient admission control. We now show some empirical results to show how Kerveros works in practice. First, we describe the alternate solutions we compared Kerveros against. The first solution is the partition technique, where capacity is reserved by partitioning machines for reservations. This solution works well in systems where there are greater control over resources and isolation, and also resource demand is somewhat predictable, so it is a great fit for private cloud. However, it does not handle the fragmentation that comes with high heterogeneity well, which leads to resource wastage in public cloud. Another approach is the placeholder, where the reservations are allocated resources immediately upon acceptance. This has the benefit of being simple and guaranteeing SLA, but the early binding to allocated resources lead to low packet efficiency in the system. So let's see how Kerveros does compared to these approaches in different aspects. First, we see how Kerveros does in terms of resource efficiency compared to others. We show the results from one of our simulations using real-world VM arrival trays spanning over multiple days, complemented with synthetic reservations. This trace contains arrivals and departures of both VMs and reservations, and we define efficiency to be the percentage of actual possible VM allocation in the system that is estimated by each policy. Here, we see that over time, partitioning gets very poor resource efficiency. Placeholder does better than that, while CRA does much better than both of them. Finally, by supplementing CRA with LAA, Kerveros does much better than all of them and achieves very high resource efficiency. Kerveros does better than all because of relying on allocable VM, which counts the number of VMs that can be placed in the system. Moreover, it leverages allocation emulation by LAA to fine-tune its admission decision. And this high resource efficiency enables Kerveros to have sufficient capacity to deal with failures in the system when they occur. From this plot of production data spanning over a month, we can see that Kerveros achieves 4 nines of availability on a consistent basis. Finally, we take a look at how Kerveros scales with the large scale of Azure using production data worth of 1 month. In this plot, we show the impact AV count computation has on allocation runtime with increasing number of machines. The lines represent 50th percentile numbers, while the error bands span between 25 and 75th percentile. We see that allocation latency is more significantly impacted by the number of machines compared to the AV count computation. This indicates that the AV count computation scales really well with increasing number of machines and do not introduce any new overhead on allocation. To conclude, Kerveros is the admission control system actively deployed in Microsoft Azure, which handles variability in supply and demand while dealing with hardware and VM type heterogeneity. It is highly scalable and resource efficient at cloud scale. And it achieves high resource utilization while maintaining SLA, leveraging late binding of reserved resources for admission control using a novel bookkeeping technique called allocable VM. Thank you.